All right. So my name is Lipo, and I've been asked to introduce our speaker today for the Compass seminar. His name is Dr. Brian Arbic. So Brian has been visiting the Rosenthal's School for a couple of days already, and as such, the Erasmus Committee on Diversity, Equity, and Inclusion took the opportunity to ask him to give us a talk yesterday about his ongoing efforts to promote DEI, notably through his Ocean Environment Summer School in Ghana and his vision for a worldwide ocean corps. So thank you again, Brian, for sharing your experience and the experience of your collaborators yesterday on this great efforts. We really appreciate it. So we could not have had a scientist of your caliber not give us a science talk, and this is what you're just about to do. So a little bit of bio information about Brian. He obtained his bachelor in physics and mathematics from the University of Michigan in 1988, and then he joined the Peace Corps and taught math and physics in secondary school, first in Liberia and then in Ghana, in Western Africa. He went on to obtain his PhD in oceanography from the MIT Woodsole Joint Program in 2000. And after a few stops on the way in Texas and Florida, he eventually came back to the University of Michigan as a faculty in 2010. And now he's a full professor in the Department of Earth and Environmental Sciences. So Brian's CV is very long, as he's had many accomplishments throughout his career so far, including a prestigious career grant with NSF. And one of his many accomplishments is also to advise and mentor so many undergraduate and graduate students and postdoctoral researchers. So Brian is known in the ocean community as the ocean tide guy, I want to say. But beyond his expertise and his academic accomplishments, what I'd like to convey about Brian is that he's actually one of the kindest and most generous scientists that I know. And I think this is exemplified by the large number of co-authors you can find in every single one of his 100+ papers that are actually published in press or submitted. I don't know if you realize, but I think you're just hitting the 100 paper mark.
I am.
So I hope today you enjoy this talk, which is quite long, but here it is. Frequency dependence and vertical structure of ocean surface kinetic energy from global high-resolution models and surface drifter observations. Thank you, Brian.
All right, thanks so much, and I really apologize that I had a lot of problems today as well as yesterday with the IT, but we should be fine now. It's a much simpler talk than yesterday. No movies, no co-speakers, just this PowerPoint. So Shen's already read the title. He's basically an equal co-author on this study because he's the drifter expert, and we brought in the models. Many co-authors. I'll just point out briefly, one other thing about the co-authors is the three others on here were actually computer science undergraduates. And anyway, so I like working with undergrads to some extent. Motivation. So ocean surface currents are important for many reasons. They impact air-sea interactions and climate, marine ecosystems, and operational ocean modeling, search and rescue missions, oil spill predictions, and all that kind of stuff. It turns out that both the frequency dependence and the vertical structure of those currents are important for air-sea interactions, interpretation of remote sensing measurements, and so forth. So there's some missions coming up that will measure velocities in the ocean surface, and so it's important to use models and drifter data to get a sense of what those missions are going to see. So here what we're going to do is examine geographic maps, frequency content, and vertical structure of near-surface kinetic energy, or KE, in drifters and two global models. So we're going to use the 125th degree HYCOM simulations run by the US Navy and 148th degree MITgcm simulations run by NASA. So both the HYCOM and MITgcm simulations include tides. So this has been something I've worked on over the last 20 years. If you put tides in a big general circulation model that also has the atmospheric forcing, then you get near-inertial waves from the atmospheric forcing, and the internal tides and the barotropic tides, and of course the atmospheric forcing drives Ekman flows and currents, and those give you eddies. So you just get a whole lot of the spectrum is added when you add tides. It gives you the tides and even an internal gravity wave continuum spectrum. So we've been comparing the high frequency motions in these global models to several data sets and many papers, including more in preparation. And just 3 years ago, I was here and I gave a talk in general about global internal wave modeling. So Today we're going to do a very specific application comparing the surface kinetic energy in these high-resolution global models that include all these motions, including internal waves, and we'll compare them to drifters. So it follows on a paper that Shen was on, you et al., where they compared only the MITgcm to drifters. And but having another model in there is interesting because there are known problems with both models. That, this model does this better, that model does that better, so you can learn a lot. Okay, so we use observations from the Global Drifter Program, which of course is run by many people, but especially Rick Lumpkin, Lucas Centroni, and Shen and others, so very well-known product here. We have undrogued drifters, which represent flows at the surface, and drogued drifters represent flows of 15 meters. A little bit about the two global models. So HYCOM has 41 hybrid layers, and hybrid coordinates were, I believe, first developed here at Rasmus by Reiner Black. You have switching between Z coordinates, isopycnal, and terrain following. MIT, on the other hand, has 90 Z levels. Since we are talking about motions in the upper 15 meters, it's sometimes asked, what's your resolution there? So in the uppermost 30 meters, there's 7 Z levels in HYCOM. So HYCOM is Z in the very upper ocean because it's not isopycnal in the mix there. And there's 13 in MITgcm, so pretty high resolution power. One big thing for the tides is that we have argued that in the real ocean, the waves break. We know that. And in these models, of course, they're non-hydrostatic, and they're the biggest global models around, but they're nowhere near enough to have the resolution where the waves actually break. So we have argued that because of that, you still have to put a knob in there. It serves as a crude damping parameter, and that will be very important when I show a couple slides on tides. That drag is not in the MITgcm. You'll see that the tides are much too large in that model.
Brian, did you just say they're hydrostatic or non-hydrostatic?
I might have said it wrong. The models are hydrostatic.
Yeah, okay. Right.
One other thing that's really important for the atmospheric scientists that we're really starting to learn that we need as much atmospheric forcing as we can. The MIT model has 6 hourly atmospheric forcing. You'll see in the near-inertial motions it's not enough. The MIT HYCOM has 3 hourly, and I'll show some preliminary results from a coupled model where you have really rapid forcing. It really makes a difference. And then, I've worked with HYCOM for a long time, and my Navy collaborators might not like that I do this, but I feel it's very important to be honest about the warts in the model. There's actually a numerical instability in the model, and you will see in certain frequency bands, it's like that is not physical. Fortunately, it doesn't affect all frequency bands, but some of them it does. So we will use frequency spectra to separate kinetic energy into different bands. We'll compare drogued drifter results to 15-meter model results, undrogued to 0-meter model results. And this is a new thing. We're actually going to just be brave and try this. We will look at the vertical structure of kinetic energy by looking at the ratio of kinetic energy in 0 to 15 meters in the models, and we will compare that to the same ratio in undrogued to drogued drifters. And I hope to convince you that the patterns are somewhat similar and worth doing. So here's the definitions of the bands used. They follow that in the previous paper, which only used MITgcm. Low frequency, less than 0.5 cycles per day, so that's 2 days. Near inertial is near F, and the diurnal period is the same numbers but near a cycle per day. So that means that when F is a cycle per day, which is around 30 degrees latitude, these definitions overlap. So that's worth keeping in mind. So there's a little bit of double counting here, and then here's semi-diurnal. So these are actually known in our community as Elipo plots, because Shen has shown them many times. So this is latitude, and this is frequency, and we're looking at undrogued versus drogued drifters, 0 and 15 meters in each model. And I'll just point out a few features. So around 0, which is this line here, that's where most of the energy is. So most of the energy in the ocean is at low frequency geostrophically balanced motions, focus on the equator, they wouldn't be geostrophic. But anyway, low frequency, eddies and currents and stuff like that. So those are still the biggest motions. The 2 cycles per day, that's the semi-diurnal tides. And then this line here is the near-inertial motions. Of course, it has a different frequency with latitude because oils turn. The other thing that's worth noting in this plot is that you'll see that the tidal lines, 2 cycles per day, and the harmonics 3 and 4, they stand above the background much more in the models than they do here. And so one of the reasons that the peaks are wider in the drifter data, we think, that people are investigating this now, including Shen and others, is that, so think about this, so imagine that there are only tides in the world, but the strength of the tides was different at different grid points. So if you have only Eulerian spectra, you'll always have a sharp peak, but it'll be different magnitude. But if you have a Lagrangian drifter, it's sampling differently sized peaks, and so then, therefore, the Lagrangian spectra actually widens up. This has been shown mathematically. And you can kind of see that here in these globally averaged spectra around the tidal peaks. The drifters are the red colors. You see the legend here, undrogued and drogued. So the drifters are kind of, there's a lot of background noise, and well, relatively speaking, and then the peaks stick up, whereas the models, it's like a real sharp peak. Okay, so part of that is just Lagrangian versus Eulerian sampling, part of it is instrument noise. And in both the Eulerian and Lagrangian, there's also an effect that the mesoscalating motions knock the internal tides around and spread the peak. That would be seen even in our Eulerian spectrum. Anyway, so one thing to note here in this global average spectra, so again you see 0 cycles per day, most of the energies in the currents and the eddies. So people who study those things, which includes me, can be relieved. They're still really important, even though I'm also intrigued by the high frequencies. Here's the near-inertial peak, which is kind of smeared out because this is a global average and F varies with latitude. Here's the tidal peaks. And so you can kind of see from this spectra that the low-frequency motions are the most important. The near-inertial peaks are also energetic with the wide peak, and then the tides are here. Another thing worth noting is that at very high frequencies, so this green color is MITgcm dark green and light green. And you can see the difference between dark green and light green, for instance, here. You don't see it here. So what that means is there is not much vertical structure in the flows. There's no difference in the kinetic energy between 0 and 15 meters at very high frequencies in MITgcm, but there is in HYCOM. And we think the difference is that the winds actually drive, like it's kind of like a high frequency equivalent of an Ekman flow. It's like you solve an Ekman-like problem, but you allow high frequencies. You still get some vertical structures. So if the winds are kicking in at high frequencies, you'll see some vertical structure. Here you don't see it because you're not hitting it hard with the winds often. So atmosphere, very important. So here are maps of the low frequency kinetic energy. This is HYCOM at 0 and 15 meters, MITgcm at 0 and 15 meters, undrogued and drogued drifters. I'm just realizing here that, are the people online actually seeing presenter view?
No. They see this.
The full screen?
Yeah, it's good.
Okay, good. Okay. I didn't want to mess with it. Okay, so when you look at these maps, we'll look first at these upper maps before we look at the vertical structure ratios. So you see the strong equatorial currents and the strong western boundary currents and the eddies that they produce. We know all these features. You see some gaps in the drifters, which Shen has just in the last week figured out a different way to analyze the drifters that closes these gaps. But that I'm not showing that new analysis here. And so if you look at these numbers here, these are correlations, spatial correlations. So this is between the models, that number shown here. And this is the spatial correlation of MITgcm with the drifters, and this is the spatial correlation of HYCOM with the drifters. So in the low frequencies, these numbers are fairly comparable. Now it's kind of interesting to look at the vertical structure maps. And so, to my eye, when you see here's this pattern of red here in the data, and then you see that same pattern of red in HYCOM and MITgcm. When you calculate the spatial correlations, they're not fantastically high, but there's a lot of points here, so these actually are somewhat high. And when you use Shen's new drifter product, where these gaps are closed, these numbers actually go up quite a bit. So there actually is correlation between the vertical structure in the models and the data. Not as high as what you see in the absolute kinetic energies themselves, but you see this. And as far as we know, no one has done this kind of thing before, to look at the structure of the velocities from 0 to 15 meters on a global level. So I should have mentioned this before. Why does that kind of thing matter? So right here at FSU, Josefina has shown that if you want to predict trajectories very accurately, you need to know not just the velocity at the surface, but not surprisingly, some estimate of the vertical structure. Another thing to note is that an air-sea interaction, of course, doesn't happen literally right here. There's some layer over which it happens in both the ocean and the atmosphere. So the vertical structure velocity matters for air-sea interaction as well. And one last thing is that when you're launching satellite missions to measure velocity, as people are planning to do right now, you measure the velocity at the surface. You want to know what that means for the velocities underneath. So probing this vertical structure is not just an academic exercise. Okay, enough said about that. All right, so that's global map. So what if you take zonal averages? Then lots of information in this paper. So the red is the drifter, the blue is HYCOM, and the green is MITgcm. This is undrogued drifters versus 0 meters in the model. This is drogued drifters versus 15 meters in the model, and I'll talk about the ratios next. So, everyone will see different things when you look at this, but the models certainly resemble the data somewhat, but probably their biggest weakness is right here at the equator. There's an awful lot of energy at the equator. And in Shen's new analysis, which closes the gaps in the equator, actually the discrepancy becomes higher. So the data actually moves up and the models are left here. So the models are not cranking out enough eddy kinetic energy at the equator. I don't know much about equatorial dynamics. Maybe someone on the call or someone in the room or call does. But that is actually, this gap right here is maybe the largest gap seen in the models in terms of absolute magnitude, because you'll see when I show the other motions, this scale drops. So the biggest motions are in this band, the low frequency band. Now, what about this vertical structure that I'm personally kind of obsessed with in this paper? So you can see there's an exception here, but when you look over most latitudes, the blue in HYCOM is kind of tracking this vertical structure. Again, that's an exception, even to the point where it goes up here. More or less, it's tracking it within fairly large error bars. And then the MITgcm is similarly decent over most latitudes, but something is going wrong at high latitudes. So I don't know. Again, everyone sees this differently, but to my eye, I was impressed that the models are kind of following this vertical structure ratio when you do plenty of averaging, like I say. In the previous plot, you do spatial correlations. It's worth pointing out that the low frequency band is not just big eddies and currents, that those may be dominant, but there's also Ekman flows. That's going to be included in your definition of low frequencies. And I just bring that up because Ekman flows have a lot of vertical structure. Okay, so turning to the near-inertial band, what you see is that there's plenty of energy in the mid to high latitudes in the models and the data. That's where the winds are blowing strongest. We can't define it right at the equator because it's based on F. This is the band where the vertical structure plots are probably least useful. The drifters are somewhat noisy, and you can see that here. The spatial correlation is extremely small. So turning to the zonal averages, now again, this scale is 10 times smaller than it was for low frequencies. But, 1/10 is still something to worry about. So when you look at the zonal averages here, the main feature that stands out in my eyes is that MIT in green is way too low compared to the drifters in red, and that's true in the northern hemisphere as well as the southern hemisphere. HYCOM does quite a bit better in the southern hemisphere and basically over all latitudes in the northern hemisphere too. But HYCOM is still not capturing this very well. And I'll show you another analysis later that I think basically suggests it's all about the winds. You know, that this is an ocean force model, 6 hourly winds. This is an ocean force model with 3 hourly winds. And I'll show you that if you run a coupled model with, you know, hourly coupling to the atmosphere, then this discrepancy here goes away. The near-inertial band is known to have vertical structure. Again, the error bars are pretty large, but to my eye, you know, within error bars, they're reasonably consistent, and it is sitting a little bit larger than 1. There is known shear in the near-inertial band, so this ratio tends to be a tad larger than 1. Okay. And then this plot just shows that the main source of this discrepancy here, even in HYCOM, it's more in the Pacific than it is in the Atlantic. So, okay. Moving right along to the next band, now you have the diurnal band. So the diurnal band, this feature here actually is a known internal tide feature. It's known that diurnal internal tides are strong right there. What's happening here and here is that is the latitude at which our definitions of the diurnal band and the near-inertial band overlap, and the near-inertial band is so much more energetic that that's going to be a dominant feature of the plots. And then here's the vertical structure maps. So one thing that's kind of interesting to me as a tide guy is I think Shen can confirm this. When the first paper was written, I don't think anything was said about whether the diurnal might include non-tidal motions. So you can actually do a diurnal tide harmonic analysis. We know how to do this in the tide community. You just look for things that have the right phase and frequency and all that. And then your map looks like this. It's pretty different. So now this is picking out what we call stationary internal tides, meaning it's literally predicted by an amplitude and phase. And so I suppose it's possible that there's a really strong non-stationary diurnal tide that accounts for the discrepancy between this and this. But these scales are log axis. So personally, I think the more likely explanation is that there are other things in the diurnal band than tides. For instance, the sun rises and sets, right? So there's a known diurnal cycle in everything. It's not just tides. When you look at the zonally averaged diurnal kinetic energy, this is one of the more interesting, zonal average plots. So, HYCOM in blue matches the drifters in red better in these bands which are dominated by near-inertial motions, and MIT is much weaker. So that's just, again, saying the near-inertial motions in the MIT model are too weak. In between those, the MIT model is actually too strong. The green is above the red and the blue. And then the harmonic analysis is way down here. It's not totally negligible, but it's much weaker. So there's a lot here. Again, the stuff that's clearly identified as tidal is not totally negligible, but it's down here. And even in these bands where the near-inertial doesn't overlap and pollute, so to speak, the signal, you can still see that the harmonic analysis is way down here. So there's other motions, again, there's diurnal cycling. So it's known that they're, again, bringing back to Ekman, when we first learned about Ekman flows, we assume everything is steady and all that, but then there's a diurnal cycle on top of it. So it's known that Ekman flows have a diurnal cycle. It's known even that sub-mesoscale eddies have a diurnal cycle. So there's a lot going on in the diurnal band. It's not just tides. When you look at the vertical structure of these diurnal things are matched in high latitudes. HYCOM in blue does a better job matching the drifters in red than the MIT model does in green. On the other hand, at the equator, it really gets complicated. HYCOM in blue isn't so good for the vertical structure, But if you look here, it's actually closer in terms of the absolute magnitude. So it's a very complicated band. And this is a descriptive paper. I'm not telling you all the reasons why things are, just this is how they are. Okay, so going to the semi-diurnal maps. So the semi-diurnal tides are known to, when you have flow over topographic features such as Hawaii, you get these strong internal tides, so that's around Hawaii, the French Polynesian Islands, the West Pacific. But this feature here is a numerical instability. That is not, it's unfortunate because there actually is a hot spot of internal tide generation there. So there's some real internal tides in here, but there's also a lot of numerical problems. The Navy shouldn't replace that. Anyway, but I won't get into that story. So you can see those hot spots as well in the drifters, and you can see them better in Chen's newer analysis, which will come about in later. Right, and then the vertical structure, there isn't a whole lot. These numbers are mostly near 1. But the spatial correlations are higher, a little higher in HYCOM than in MITgcm, and when you use Chen's new analysis, that discrepancy is even greater. So when you take zonal averages of the semi-diurnal tides, so maps, zonal averages, that's what we're doing. It's kind of interesting. So the green MITgcm is way above the drifters in red. HYCOM is somewhat above the drifters. And this feature here is almost certainly dominated by that numerical instability. And the vertical structure ratio is pretty close to 1. So we are submitting a paper soon where we've shown that when they ran this MITgcm simulation, they made mistakes in the tidal forcing. But being tide guys, we can estimate how much that matters. We think that's about a 17% effect. And you can see that this discrepancy is more like a factor of 4 effect. So that mistake in the forcing is not going to change this. We think the bigger thing, again, which we've argued for 20 years when you're running these models, is that you make the waves, you don't break them in the model. You have to have a knob accounting for that. And here's a somewhat debatable thing to do, but I'll do it anyway. If you remember, I said and we showed that the Lagrangian spectra are wider. So what we're doing here is we're saying, what if you take this definition of the semi-diurnal band and just widen it out? And like magic, what happens is the models don't change that much because remember the peaks were really sharp. But like magic, what happens is the drifter levels are lifted up, and so there are a lot of latitudes where the drifter levels are actually fairly comparable to HYCOM. And I would argue that maybe that's a reasonable thing to do because we're not actually doing apples to oranges. We're not doing apples to apples here. So what we really need to do is release drifters in the model so that you're really doing an apples to apples thing, but that's a fair amount of work. We haven't done that yet. So I'm actually almost done with this first quick part. So discussion of vertical structure is the first part of discussion of vertical structure. So momentum input at the ocean surface mixes downwards. So this is controlled by the KPP mixing scheme in the models examined here. Chen showed in his thesis that yields a frequency-dependent shear that's a minimum at the near-inertial frequency. So there's a lot of complicated stuff in here, but just saying that that's part of what's going on with this vertical structure is that stuff that's directly input by the wind, it's going to mix downward. The KPP mixing scheme will have something to say about what happens. And again, a reminder that the wind-driven motions include Ekman and near-inertial flows. It's been known for a very long time that those have vertical structure. There are motions in the ocean that are not directly wind-driven. So the Gulf Stream isn't directly wind-driven. We all remember that the wind drives Ekman flows, and then through a chain of reasoning, you get the Gulf Stream out of that. So you might think that for low-frequency motions like the Gulf Stream and eddies, and also for semi-diurnal and diurnal tides, it might be useful to calculate the classical vertical normal modes. So we did do this. We calculated the classical vertical normal modes from about 6 points across the globe spread out by latitude. And we just looked, is there any vertical structure in the 15 meters in those classical vertical modes? It's basically very, very little. It's like in the third decimal point. So the semi-diurnal tides don't have much vertical structure in the models or the data. To within error bars, they're all basically like 1. And people think the semi-diurnal tides can be described by these classical modes, and the classical modes don't have much vertical structure. So there's some consistency here. The total, now the diurnal tides have less, the true diurnal tides, which you calculate from the harmonic analysis, have less vertical structure than the total diurnal motions. So we think that the total diurnal motions have structure due to non-tidal effects. That's what we mentioned those earlier. There's near-inertial flows where they overlap, there's diurnal cycling of vector flows. So the conclusions from this submitted paper, but I'm not quite done with the whole talk yet, is that drifters provide a global data set to discriminate differences between models. More frequently updated wind fields provide greater near-inertial energy in HYCOM and a closer agreement with drifters than you see in the MITgcm run. The tidal KE is much too large in that MITgcm run, and we think that's due primarily to the fact they're not parameterizing the damping that happens in the real ocean. And you can get a better agreement in the tidal, but semi-diurnal tidal band and HYCOM and drifters if you widen the thing out, which we argue maybe is reasonable to do for the reasons I mentioned earlier. And then I think it's cool that the zonal averages of the model 0 to 15 meter KE track latitude and frequency dependence in the same ratios computed from undrogued to drogued drifters. So ongoing in future work, we're going to look whether the near-inertial flows are stronger and closer to observations in coupled simulations. I'll actually show you the preliminary result from that in a second. And on the Navy side with HYCOM, we want to compare the drifters to assimilative simulations, but that second one will take a little bit longer. But showing a first results from analysis of a coupled model. So this is the thing, everything I've shown you so far is in a paper that's submitted. Now we're kind of working on the next one. So the grid spacing in the ocean, in the coupled model, is the ocean part of the coupled model is a little bit less. It's MITgcm. It's less fine than in the MITgcm driven model. They wanted to go all the way up to 148, but they actually said that they just couldn't quite get it to run on mass computers. So they were going to have a global. They're planning a global 132nd atmosphere, 148th ocean, all running at once, and they just couldn't get it. Dimitri said they broke the computers. For those in the atmosphere side, you probably know Mandarin a lot. She's involved in the project too. Anyway, so when you look at the coupled model at the very high frequencies, the difference between 0 and 15 meters, now you see some vertical structure here. So again, our first thought, which we're going to test out with Shen, is that again, when you have a coupled model, you're coupling it very frequently. There actually is very high frequencies in the winds, and they can drive kind of an equivalent of an ecton flow at high frequencies, and there is vertical structure. We'll test that out and see whether the theory matches up with what's seen in the model. The higher resolution MITgcm has more energy. It's resolving more of the very high frequency internal wave energy, but no vertical structure compared to the coupled. And then here from green to blue, you're going from uncoupled MIT to coupled, and so you're getting closer to the right value from the drifters on the equator. So having more frequent coupling seems to impact not only near-inertial flows, which I'll show you in a second, which is fairly obvious that it should happen, but it even affects the lower frequency flows. Although it gets confusing because near the equator, the low frequency, F is 0, and so you're kind of also near-inertial. Well, I have to think about that. But then this thing here shows that this is the uncoupled MIT, and this is the coupled MIT, and look how it's a lot closer to the drifters. Now this kind of stuff matters for design of satellite missions. So right now, right now people are designing a waves and currents mission to measure currents at the surface. And there's a big question, you know, these near-inertial flows, the kinetic energy is like 1/10 in the global average of what you see in the equator. That's in low frequencies, sorry. But in higher latitudes, it's a higher percentage, and so what you want to do really is get rid of this signal so that you're only seeing the eddies and the currents. And so it's important to have a model that has these about right so that you conduct OSSEs and look at how bad the aliasing problem is. So this is actually, the fact that this agrees with the drifters is actually quite important for NASA. I mean, just last week I gave this talk and the lead of that mission said we need to talk basically because of this result. So I was also going to show one more, just a few quick results from another paper, and I'm just kind of wondering whether I should do that. I started late. Should I just skip that or should I zip through it?
Well, it's 15 minutes left in the hour, so if you 5 minutes.
Well, you're going to like it, or it's going to interest you.
I'm open-minded, Brian, but
Yeah.
I think there's time left, so go ahead.
Okay, so this also has another Rasmus connection, not Shen, but Ben Kirkman. So this paper here that I'm going to show you real quick is only related to everything that I've shown you in the sense that this exact same coupled model is part of the study, okay? But otherwise it's pretty unrelated. We're looking at rainfall. How did an oceanographer like me get involved in looking at rainfall? And the answer is that, you know, models, these big models don't just have internal waves, but they also have eddies. I've written a lot of papers about eddies. And there's this idea that many of you probably know about, that if you run even, say, a weather class model, but you actually resolve the ocean pretty well, then you resolve those little spinning eddies which have SST signatures, which therefore might affect convection and rainfall. You know, I mean, weather models work pretty well, but there's this idea out there that maybe resolving the ocean will give you a little bit of an improvement in the skill at maybe like 10 to 30 days or something like that, for the reasons I just said. So kind of motivated by all that, we started looking at rainfall. And what I'm kind of proud of by this is that, one thing I'm proud of here is that this paper was led by an undergraduate computer science major, this guy here. So this is another many author paper. You can see that Leo and Ben are on this paper, because theirs are among the models we looked at. So we're looking at effects of grid spacing on high frequency preset variance in coupled high-res models. So I'll have to be fast, but the gist of it is that higher resolution does seem to make a difference at the high frequency end of precipitation variance. So we all know, even from personal experience, that precip often takes place in brief but intense events. And please someone tell me if I'm wrong, but as far as we can tell, this new class of models where you have high-res ocean, high-res atmosphere, and they're coupled, people haven't looked at the high frequency precip variance as far as we know in those models. Okay, and again, the argument is that eddies could affect the atmosphere. So real quick, you know, we do look at TRIM and CMORPH, which are satellite products. When I write the next paper, we should use, I think it's called GPM as the new mission. We look at a few rain gauges over the ocean, this one here, and a cluster of NOAA rain gauges in this part of the country, the US South Atlantic. It's kind of a hodgepodge of things we looked at. We looked at a reanalysis from ECMWF ERA5. We do have a weather model in here. The US Navy ESPC is actually a coupled ocean atmosphere where both fluids have data assimilation. And then we have a bunch of non-operational, fairly high-res coupled models. And again, it's just kind of what we could easily get our hands on. So the NOAA GFDL, they had a half-degree atmosphere. That's fairly low resolution for the atmosphere. But they had different model grid spacings as shown here. CESM kind of similar. They had different oceans, but they had a higher resolution atmosphere, and that would matter. And then there's that NASA model. It's not even the newest NASA model because this project started a few years ago. But at that point, they had this going on. So one thing that you can see in an example precip time series at this particular site here is there's what's people call the drizzle effect. That the real world often sees days with zero rain. Models tend to have a lot more days where there's just a little bit of rain. They don't seem to, they have a harder time having days with literally no rain. Okay, so that's one thing to know from this time series. Now, the first thing we did is we did this variance analysis of Covey, Trenberth, and others. And in that paper and a few others I read by Trenberth, they even suggest that even looking at sub-daily precipitation variance isn't that common, even looking at data. But here again, I'm not an atmosphere person, so others can chime in if I'm wrong there. But or if Kevin's wrong. So basically, what they do, without getting into any details, they take a particular month and let's say many years of that month, and from that they can define a typical, let's say, June 1 versus a June 2 versus a June 3. So you can talk about daily means, you can talk about a mean diurnal cycle, and an overall monthly mean. So when you look at the variance, there's a variance due to the fact that the mean of different days isn't the same. There's a diurnal cycle, and then the residual of all that is something they call irregular subdaily variance. So that's basically something that's below diurnal periods. And so here's a few basic results from the paper. So when you look at here are maps, and here are zonal means from CMORPH. Here's the irregular subdaily, the daily means, and the mean diurnal cycle. Notice these are standard deviations. So if you square that, then the discrepancies get even larger. Because note that the irregular subdaily is 10 times larger than the diurnal mean. So that's one of the points Covey and Trenberth are making, is that you can see a diurnal cycle, but this irregular subdaily is much bigger. And the other thing that you're seeing here, you're seeing TRIM and CMORPH and ERA5, and they're all fairly close to each other. This non-assimilative model is down here. So I wanted to show you a plot from the Covey-Trenberth paper, but they looked at a low resolution CESM model, and it was way down here. It's basically not capturing this irregular subdaily stuff.
Brian, I gotta ask, when you say mean diurnal cycle standard deviation, that's the amplitude of the diurnal cycle, or the variation of the diurnal cycle, like from day to day or time to time? It's got to be the amplitude of the diurnal cycle, right?
Good question. It's if you're taking all of the variance and saying how much of the variance is due to the diurnal cycle.
Okay, so that's amplitude of the diurnal cycle.
Yeah.
Yeah. All right.
Right. But but we're showing standard deviation. If we showed variance, all this stuff would be squared.
Right.
Yeah. So when you look at the some of the models we're looking at here, like I say, this particular model here is too low, as you can see. And the Navy model actually is pretty close, and maybe that's not surprising because it's a weather model, so it's assimilating things like CMORPH. The NASA model is actually way too high. So, again, it's kind of a hodgepodge of models, but again, a CESM climate model type resolution is way down here, and the NASA model is way up here, and like weather models and ERA are sort of just right. Now, it's interesting that we looked at a lot more models for this paper, but we could not do this analysis for most of the models, and the reason is because most models don't save subdaily output. So that's one of the points of the paper, is that if Trenberth is saying and Covey are saying a lot of the variance is subdaily, it's a bit of a shame that our models don't save subdaily. But of course, part of the reason they don't is a lot of these are actually climate models, and so we're moving towards a future where climate and weather models are coming together, and we can do these kind of analyses more. So since we can't do the Covey analysis with most of these models, we turn to frequency spectra and CDFs. And I'll go a little faster here, but if we look at CDFs, things like, these are a fraction of days where you have a little bit of rain in CMORPH versus the models. You can see that the models, they're mostly dark, and so they're having a lot of days with more than a little bit of rain. So that shows you that drizzle effect, that even these high resolution models that look better in other respects They still just have too much drizzle. And looking at a couple frequency spectra, I'm just trying to give you a little bit of an idea here. So, there's a lot of stuff on here, sorry about that, but the rain gauge is, this solid orange line. And so this is a very high frequency rain gauge. So this rain gauge is a solid orange line. You can see that the reanalysis from ERA5, which is this line, and CMORPH, they're below the rain gauges. There's a smoothing of, I think, they're working in satellites in a totally different context. I'm just going to guess that all satellites have a certain amount of spatial and time smoothing in order to make global maps, and so they tend to lose variance at the high frequencies. You still see the diurnal peak. And then that NASA model ends up sitting way too high. So there's the highest resolution model has too much variance compared to the rain gauge, and some of the other products are too low. It's kind of the point there. And there's, sorry to make a point with the table, but one thing you can see here is that this is in a particular region of the Northwest Pacific. If you look at the GFDL class, notice how the variance in this particular band that we use, which I forgot to mention, is between 2 and 100 days. It doesn't change that much, but it does increase a little bit when you increase the ocean model resolution. But you look in CESM here, there's a bigger change, and again, it's a bit, the whole analysis is a bit hodgepodge. It's in a different region. But we think part of the reason you see a bigger change when you increase the ocean model resolution with this particular CESM thing, this difference is bigger than these differences, is because the CESM has a higher resolution atmosphere. So if the ocean model resolution is going to matter for those SST causing convection, well, if you have a 1/2 degree atmosphere, it's not really going to see that. The atmosphere doesn't have enough resolution to see what the ocean is doing. Too much smoothing. So I went through that probably way too fast, but the point is that a decrease in the grid spacing of atmosphere and ocean models does seem to generally lead to more precipitation variance at high frequencies, sometimes too much, as in the NASA model. The ocean model grid space seems to matter more when it has an atmospheric model with enough grid spacing to feel that. And all the models have a drizzle effect. And again, all these things are connected because, if that NASA mission goes up and measures surface currents, we'll have a better understanding of air-sea interactions. Air-sea interactions, obviously, precipitation is a big part of that. So someday I might actually understand how all these things fit together. But that's all I have to say.
Okay. All right. Thank you. Questions online?
I don't see any, but you can ask from there and ask them to
Ask if there are
turn
questions.
their
Fine.
microphone and camera on.
It's like 2 things in the chat, maybe you want to say?
No, there is nothing in the chat. Josefina has her camera on. Maybe she wants to ask something.
Oh, Leo has a question. Sorry, it took me a minute to get to this. You want to ask something, Leo?
Yes, sure. Thanks for saying that. So for the ocean paper, the kinetic energy one, when you say that the low frequency band you're using, you said is it longer than 2 days and everything longer than that?
That's the definition we use, yeah.
Okay. And then the second question I have is tied to this one is, so those are ocean model only forced by atmospheric forcing. So which is the atmospheric forcing used for those high-res HYCOM and MIT?
In that case, the MITgcm was forced by an ECMWF product.
Okay.
And HYCOM was forced by, of course, a Navy weather model, which is called NavGen.
Okay. In the Navy, okay. In the Navy model, is it like a very high resolution atmospheric model? I mean, weather.
Well, it is what they use as a weather model out of NRL
Okay.
Monterey, whatever. Maybe some here. It's written in our paper off the top of my head. I can't.
Okay, I'll look at it. And just
Yeah, I seem to recall it's of order a quarter degree.
okay. I'm just trying to make sense of what you said about the equator region having like a too low, kinetic energy for the surface layers, let's say so. So I was wondering if it's related to wind bursts that are not somehow in the forcing fields you gave to the ocean model run, and then maybe the couple of models have more, say, those internal variability in the atmosphere, like noise, and then they can be really strong, and then they would work from 2 days to a couple weeks, say, let's say, synoptic scale in the equator region. And those can be pretty strong, and then they can probably force stronger, surface current or near surface current that is not being captured. And some of them are really not zonal in nature, so maybe if you just split and see if you have more energy in the zonal direction than the y direction, maybe it can give a hint that maybe those wind bursts are responsible for that gap. I don't know.
That's fantastic. Yeah, we should look at that. So what is the time scale of the westerly wind bursts again?
Oh, let's say from 2 days to a couple weeks. I mean, roughly.
2 days to a couple weeks. So why would a 6-hourly product not capture that? Is too much smoothing, you mean, or?
Yeah, if the resolution, as you said, like a quarter degree in the atmosphere, I don't know what is coming from that product to the ocean. And although you're coupling every 6 hours or so, it's just not there. This internal atmospheric variability is not there. So, I don't know. But this is just a guess. I'm just trying to make sense of it. But
That's good. So Shen has a...
Can you ask Leo if these wind bursts are interannual in nature, or do they happen every year?
Shen is asking, maybe you heard him, Shen is asking whether the wind bursts are interannual or not.
well, you can have like from intraseasonal, seasonal scale things, but I would look into those more fast, like from a couple of days to a couple of weeks, like that are more energetic and then can be responsible for those peaks and not being resolved, in the products that you're using to force. But that's why I ask. It goes all the way to low frequencies, but the most energetics I can think that can maybe steer eddies, really accelerate currents in the equator would be in that range. But I don't know if you plan to look into it at some point in the future. Just
we are thinking about it because one thing that's worth keeping in mind for aficionados of satellite remote sensing. Remember, I talked about how we divided into all these bands because we're oceanographers. We like to understand all the bands, but the scale was biggest for the low frequency motions, and the biggest signal in the zonal average was the equator. So basically, that is the biggest signal.
Yeah, because I
biggest
expect
signal
that.
is the currents on the equator, so it's worth trying to understand it better for sure.
Yeah, it is. I believe that the forcing has the interannual and then like lower than seasonal frequency motions in the atmosphere pretty well represented. Just because, but then because we lack resolution, they may really be missing this high frequency synoptic equatorial scale things from 2 days to 2 weeks. I don't know. It's just.
Yeah, that's great.
Thank you.
Great point to think about. Yeah. Any others? I don't know why
Where's your talk?
Yeah, good thing it's over. Well, we are near the top of the hour, and it was my bad that we started late, so I don't see any other questions on mine.
Okay, thank you, Brian.
Yeah. Thank you.